What's going on, YouTubers? Welcome back to another MicroVid. I'm Dr. Brainerd, and in this MicroVid, we're going to be talking about hysteresis. What is it, and why do we care about it? So let's jump right into it with the slide where I talk about hysteresis in my lecture notes. So this slide is one that I made, and if we look at what hysteresis is defined as the physical. It's when a physical property lags behind the changes that are causing it. Okay. It's when the physical property lags behind the changes that are causing it. And the example of why this is important I gave is here in the lungs. So say if we have, for instance, say if we have a collapsed lung, okay? So our collapsed lung, the transpulmonary pressure is essentially going to be zero, right? A pneumothorax where the TP, the transpulmonary pressure, is zero. Because what is transpulmonary pressure? It's the alveolar pressure minus the intrapleural pressure, right? And we get a pneumothorax when those equal, when the intrapleural pressure equals the alveolar pressure. Therefore, the transpulmonary pressure would be zero. So let's look at this. So if we've got a transpulmonary pressure of zero, zoom in right here, right where that red dot, I'll do a green. We'll do it right there where that green dot is, right? We're right there. So what we're going to do now is we're going to increase the transpulmonary pressure of that collapsed lung. We're going to increase it to 5, okay? So we increase the transpulmonary pressure to 5. Do we see a change in lung volume when we've increased it from 0 to 5? No, we don't see it. We really don't see any change. I mean, maybe there's a minuscule one, but we really don't see a change. Now, when we change it from 5 to 10, do we see a change? Yes. Now we start to see a change, right? We start to see a change, but that slope in which it goes is actually becoming more steep, okay? Do you see that? So that means that if we zoom in here, I think I'm already maximally zoomed in, but if we look at just from 7, essentially right there, to 10 on the transpulmonary, on the x-axis for the transpulmonary pressure, we see a very large increase. But when we went from 0 to 7, there was really no increase at all, or minuscule at best. And so if we go from 0 up to about, what, 12, somewhere around there, right there, 12 where that black dot is, we see that we shoot up to a normal level, which is FRC, okay? So all that to say is, remember what hysteresis is. It's when the physical property lags behind the changes that are causing it, right? We're increasing transpulmonary pressure, okay? From 0 to 3, nothing happens. From 3 to 5, still nothing happens. From 3 to 7, really nothing happens, but we're steadily increasing pressure, right? And then finally, when we increase pressure from about 7 to 12, boom, that's when we get those volume changes. So even though we were changing, right, the transpulmonary pressure early on from 0 to 7, we didn't see any physical change, increasing lung volume, until we actually got to that 7 to 7 and upwards pressure. Okay, so another example of this, I don't know if you guys have like a thermostat that would that you click on. So say old school thermostats. I'm not talking about like the Nests or anything now that they have all the digital ones, but an old school thermostat where they had that little dial on the right hand side. Okay, a lot of times when you would push that dial up or down, depending on if you wanted heat or air conditioning, it would take a couple of seconds. You'd wait, 1,000, 2,000, 3,000, and then boom, you would hear the air conditioning or the furnace start to kick on. Okay, so that's an example of hysteresis in a non-biological way. Another example of hysteresis is when you have those balloons, right? When you have one of those little small balloons and you're increasing your pressure from 0 to 5 millimeters mercury, right? Nothing happens. 5 to 10, nothing happens. And then finally, when you go from 10 to 12, or maybe it's 15 to 20, boom, you get past that sort of that barrier phase, if you will. I don't know what to call it right there, but you get past that where the pressure now can overcome the resistance, and you get an inflation of that little balloon, and then it suddenly becomes super easy to inflate it. Okay, another example is like a domino effect, right? So if you've got dominoes, 1, 2, 3, 4, 5, 6, 7 right here, and you knock this first domino over, right? What's the first domino do? Well, it has to knock this one, then it has to knock this one, then it has to knock this one, and it has to go through the entire chain before the last one is knocked over, and maybe it rings like a bell. I don't know how to draw a bell right here. Maybe there's a, there we go. That's a horrible bell, but maybe it like it dings a bell or something. So there's like a little bell. So it's going to, from when you started it to when you ended it, there's a lag time there. And that's exactly what we're talking about when we talk about hysteresis. It's when the physical property lags behind the changes that are causing it. And where you'll see that and why it's pertinent in the respiratory system is when you have a collapsed lung, or you have maybe a partially collapsed lung. You're changing the transpulmonary pressure, but you're not reinflating that lung yet. You're changing it more, right? From 0 to 5, and then from 5 to 7. You're still not changing or reinflating that lung, but finally when you hit 7, when you go from 7 to 10 or 7 and above, then you start to see some of the reinflation, okay? Hopefully that was helpful for hysteresis. If you have any questions or comments or snide remarks, please let me know. And as always, y'all, stay cool, stay in school, don't do drugs.